Alright, we're going to talk about some algebraic methods for solving systems of equations. We just got done looking at a bunch of definitions and just sketching a graph and looking at how the solution to a system of equations is the intersection point. Well, here, the algebraic method, the one we're going to talk about, is called substitution. And with the substitution method to solve a system, basically the idea is this: at the intersection point, the x values and the y values are the same between the two systems. So at the intersection point, you have the same x value and you have the same y value solving each equation. And if they're the same, then you could substitute one for the other. And so if you were to solve, let's say, the top equation for a variable, we'll go with a y here. Then if you solve for y, you can take the resulting expression and plug it in for the y in the other equation, because the two will be the same at the solution, at the intersection point. Okay, so that's just the idea. So here, let's go ahead and solve for this y. The reason I'm going to take this y over any of the other variables is because its coefficient is 1. And you know that at some point when you solve for a variable, you will have to divide by its coefficient. So if you solve for a different variable, say this first x here, you'd have to at some point divide by 3, and that's going to create some fractions. So I'm just trying to avoid that scenario. So I'm going to divide everything, or avoid having to divide anything by solving for this y. Alright, so let's take the first equation, 3x plus y equal 10. We'll solve for y, so I'm going to subtract the 3x from both sides, and I get y equals 10 minus 3x. Remember that these are unlike terms, so they cannot get combined. Now, we're going to take the second equation, which is 2x minus 2y equals 12. Now, instead of putting a y in here, I'm going to replace the y with the new expression for y that we just found. So I'm going to leave a little space for that, and then I'm going to put my equal to 12. Okay. And now this 10 minus 3y, or I'm sorry, 10 minus 3x is what's going to go in the parentheses there in place of the y. Okay, so the structure is still the same. 2x minus 2y equals 12, where the old y becomes the new y, this expression. Okay. Then we're going to distribute and solve. So we get 2x minus 20 plus 6x equals 12. That's 8x minus 20 equals 12. Add the 20, you're going to get 8x equals 32. And divide out the 8, and x will equal 4. Okay, now we take that 4, and remember, the solution to a system of equations is going to be an intersection point. It's the x-y combination, or ordered pair. And so I have the x, but I still need the y. So we're going to plug that x in. We can plug it into either of the original two equations. Remember, at the intersection point, the x values would be the same and the y values would be the same. So if I plug this in, this 4, into either x, I will get the same value out for y. So I'll just choose the top one because I think the numbers work out a little better there. So let's go with 3 times my number for x plus y equals 10. My number for x was 4, so I'll put a 4 up there. And then we just simplify this. 12 plus 4, or 12 plus y equals 10. Subtract the 12, and y would be a negative 2. Alright, so final answer is going to be the point 4 comma -2, and of course because we're solving with equations, we want to use a solution set to represent this answer. So we're going to surround this thing with set form, set notation. Okay. All right, we got a couple more examples here. I'm going to burn through them a little bit more quickly. Sheet of paper. Okay. So next example, this is one where we don't have the same luxury we had in the last equation, or last example, because here I don't have a coefficient of 1, and so I can't just solve for the variable whose coefficient is 1 and eliminate all fractions. I'm going to have to create some fractions here. Now if I look at these these 4 variables, I can solve for any of them. I don't have to just solve for y. It could be an x, and it could be in the first or second equation. So it doesn't really matter, except again I'm going to try to eliminate as many fractions as I can. That's just my personal preference. And when I know that if I divide by this 3, it'll create a fraction with this term but not with this term. So maybe I'll just try that x. All right. So I'm going to take this with another color. Let's start with 3x minus 5y equals 3. And let's try to solve for this first x. So we'll add the 5y to both sides. We'll get 3x equals 3 plus 5y. And if I divide by 3 on both sides, it distributes on the right. And we get x equals, well, 3 over 3 is 1. And then we get 5/3 y. Okay? So now we're going to take that 1 plus 5/3 y, we're going to substitute it into the x in the other equation. Remember, you have to go to the other equation so that you're solving both of them. So we get 15 times my new expression plus 5y equals 21. Substitute this new expression in for the x, 1 plus 5/3 y, and then we distribute the 15. 15 times 1 is 15. 15 times 5/3, well, 15 divided by 3 is 5. And 5 times 5 gives you 25, so that's 25y. And then we combine our like terms. 25 and 5 makes 30. So we have 15 plus 30y. Subtract your 15. 30y is equal to 6. Divide out the 30. Whoa, getting low on the page. There we go. And y should equal 1/5. Remember though, I said that just solving for one variable isn't enough. You need the second variable and the entire ordered pair. So I'm going to take that 1/5, plug it back in. Maybe I'll go to the top equation again because